The impacts ring the moon like a bell, indicating pulverized rock immediately below the surface, rock that reverberates. But the moon is solid, its core metallic. The astronauts return more than 380 kilos of rock to Earth. The samples are either volcanic or the product of impacts. (1998) and the Lunar Prospector mission. Prompted by these geological maps from an earlier survey, the hunt is on for lunar ice. This image hinted at the possibility. The circle is the Aitken Basin, a huge depression at the South Pole. Prospector's sensors verify the hunch. Aitken has millions of tons of water, but deep frozen and locked up in rock. It's the same story at the North Pole. The last astronauts left the moon in 1972. With water confirmed, they'll be back. The sun is the light of our lives, radiating with the power of 400 trillion watts. Each second, it converts 4 million tons of mass to searing energy. It emits heat and light, everything from X-rays to radio. But as hydrogen is converted into helium, and as gas flares into space, a less tangible emission blows from the sun. The solar wind, a continuous stream of electrified particles. They take up to 4 days to reach Earth, but they don't touch the planet. We're protected by our magnetic field, the magnetosphere, a great bubble that deflects the solar wind like the bow wave of a ship. Normally, the wind blows at up to 400 kilometers a second. But massive solar ejections like these can boost it to storm force to 800 kilometers a second. On Earth, they cause geomagnetic storms, knocking out power lines, blacking out cities. And they can send satellites into a spin. When India lost a communication satellite, the stock exchange shut down. Mass ejections from the sun are infrequent, but here, with the solar disk masked, there's no mistaking their power. As an ejection hits us, the magnetosphere is squeezed. We suffer a geomagnetic storm. Between these major eruptions, the sun emits a steadier stream of electrified particles. They get near Earth only around the poles, where magnetic force lines funnel them toward the planet. The result is the lights of the aurora. From satellite, this is the aurora borealis, an oval of electrified particles reacting with our upper atmosphere. The aurora borealis circles the northern polar regions. Toward the South Pole, it's the aurora australis. From ground level, it's the stuff of dreams. We're watching the effect of electrified particles spiraling down magnetic force lines. They're colliding with atoms and molecules of oxygen and nitrogen. As their intensity changes, so does the color. The aurora. Every so often, when planet Earth lines up with the Moon, we enjoy another celestial spectacular. Since ancient times, these shows have beguiled us, for the main player in the alignment is that light of our lives, the Sun. It's the blocking of sunlight in an alignment that causes an eclipse. The intervening body, in this case the Earth, casts a shadow. To understand the mechanics of an eclipse, we start with an eclipse of the Moon. The Moon's orbit around Earth is inclined by 5 degrees to the horizontal, to the ecliptic. In each 27-day orbit, the Moon twice intersects the ecliptic, points we know as nodes. Here. And here, with the Sun shining from lower screen, an eclipse occurs only when Earth and Moon align at a node. A lunar eclipse and a solar eclipse. With the Sun shining from the left, the Moon moves into the shadow cone of Earth, here in white. The result is a total lunar eclipse. The Moon goes red. The cause is Earth's atmosphere. At totality, it bends and filters sunlight to project a red blush. Now, an eclipse of the Sun. But because the Moon's orbit is slightly elliptical, this eclipse isn't total. The Moon is at its farthest from Earth, and the shadow cone doesn't quite reach us. So from Earth we see an annular eclipse. The Moon's too far away to completely cover the Sun. That's always the case on Mars, where the tiny moon Phobos gets nowhere near a total eclipse. This one does. The Moon is close enough for its shadow cone to sweep the Earth. Here's the shadow of the August 1999 eclipse racing across Europe toward the Black Sea. From satellite, another shadow path. At its slowest, the shadow cone travels across Earth's surface at the speed of Concorde, 2,000 kilometers an hour. But it can go 3 times as fast. In 1998, it scoots across the southern Caribbean as Earth, Moon and Sun align. The island of Curacao. Enthusiasts from around the world assemble for a total eclipse of the Sun. Cameras, telescopes and binoculars are fitted with special filters. It's the only way to safely observe the Sun. First contact.
Look at the sky.
But as the Moon edges across the solar disk, clouds threaten the show. Conditions clear, this partial phase lasts an hour and a half. Binoculars project a twin image of the crescent Sun. Totality approaches. The Sun is totally eclipsed by the Moon. Quickly, off with the filters. For 3.5 magical minutes we can see the corona, the outer atmosphere of the Sun. The Moon exactly covers the solar disk. It's 400 times smaller than the Sun, yet 400 times closer to us. And there, with the eclipse, the planets Mercury and Jupiter. The diamond ring, and totality is over.